Okay, welcome to this week or today's stream, I guess. We're going to be looking at doing HLS, a DMA on a PYNQ platform. A quick overview, I guess. The PYNQ is kind of this Python software on a Linux operating system, usually running on a Zinc or Zinc UltraScale Xilinx FPGA, and allows you to interact pretty effectively with the hardware. So you can use Python to do hardware testing, to execute hardware accelerators and whatnot. And today we're going to show a very simple HLS module that we're going to use DMA to do rapidly delivered inputs and receive outputs. Doing this on the PYNQ interface, we can see how easy the PYNQ interface is. So things we need to do. Okay, so here's kind of a quick overview of where this video is going to go. First, we're going to show you what the HLS does. Then we're going to add the hardware while the bit file is building. We're going to go over all the HLS pragmas. How do you spell it? That can't be how you spell it. Me being blind. That's pragmas. Cool. We're gonna go over the HLS pragmas. And then we'll show you what code is required in PYNQ to execute that as well. Okay, so let's move along then. So minimize that. We're going to go to HLS. Which one's HLS? The first one. Oh yeah, it's here. So this is a very simple adder. We have an in stream, we have an out stream, input, output, stream interface, and then we have this value to add, which we can access over Axie Lite. And it adds the value to the input and the kind of the index of that in your packet that you sent. And I can show this as we move forward. And yeah, that's the simple HLS. We've already constructed it. So let's get building in the hardware real quick, and then we can get to here. There we go. Adder. And if you go to like solution and do implementation. What was the issue? That's what I get for not reading. So let's remove. So I assume it's not built for the right device. Oh, we did build it for a drastically different device. So what we need to do is we need to go, and you see that right there. We're doing a 7ZU. The ZU104. So let's copy that real quick. Go to HLS, and we want to go to solution settings. We want to change this. We can probably go boards. Go to the ZCU104 board. Boom. That's the board we want. Period of 100 megahertz should be fine. Boom. So now we're going to have to build it real quick. It shouldn't take long, and then we'll package it. And we'll go through all this stuff in a bit. Okay, cool. Super easy, latency, interval. Now we're going to package it. We don't need to do any of that. Yep. And it should be packaged to the output. Be under implementation, there's an IP folder. And be done. Cancel, we go back to IP catalog and refresh all repositories. Boom, it's now there. Let's add it to the thing. Add to IP block. Boom. So this is going to be fairly straightforward. We'll delete that. Run these connections. 100 megahertz, exactly what we want. Go for it. So we've added it. We have the same clock for all these interfaces, so that's easy. In-stream, out-stream, control clock, and reset. Okay, everything's happy. Got it. There, DMA feeding into the HLS right there. Then we have this AXI port. Now let's just make sure that called top function, right? Yeah, it's called. We don't need to worry about that one. Top function's at 8001. Seems like a good location. No reason to change it. So we want to generate the bit file. So we're going to first validate our block diagram, and then we'll let it run along so we can generate that. We'll have to update our hardware handoff file later. We probably can find it soon as this is running and get that moving over. Okay, validation successful. Boom. So now we're going to hit generate bitstream. And this will generate while we go talk about our pragmas. Oh. And that should be good. So let's talk about three things. One, we're going to talk about olefin pragmas. Then we're going to talk about what the output means here, and then we're going to go to analysis mode to look at what is being performed. We won't get too much out of that, but let's go ahead and look at what's happening. So we define our AXI stream. We have 32 bits of data and a bit of last. The last is important for DMA because DMA needs to see that last at the end of a transaction, or it throws an error. And simply we just pass along the last in our setup right here when we do the HLS. But that's something to consider when you do DMA and HLS. So we have our input stream, our output stream, 32 bits, and then we have an int value to add. So we'll talk about how we can change that value to add. So first, we have an HLS interface pragma. So we want to do an AXI-like connection, register it, and it's going to be port value to add, and it's going to use the control clock. So what this does, it makes value to add accessible over a slave AXI-like interface, and the clock that's used to write that value is the control clock, and not the main interface clock. We have a default clock right here. Next we have HLS interface AP control. So AP control none means that there's no start bit, there's no end bit, there's no status bits. We don't need that. We want to push in data, we want to get out data. So we don't need any additional single bit inputs into our HLS at the block level. So we have two AXI stream interfaces. AXI S is AXI stream for the input and the output. And then we are pipelining our system, telling it needs an initiation interval of 1. And we want to enable flush. Enable flush means that when there's no valid input, it will still continue to process anything that is in the pipeline. And yeah, so we have a quick static value that remains the same between function calls. We take our input, we add value to add, we add this number of words variable, and we save into our output data. And if it's the last one of the packet, we're going to reset number of words 0, else we're going to increase the number of words. And this way we can see the number of words that are in each transaction as that value is being added to the values inside it. And yeah, we can just simply do zeros or something like that and see it count up. So yeah, a fairly straightforward value. So when we run synthesis, HLS synthesis, so when our implementation, we gave it an estimated clock of 10 nanoseconds period. It said it can do it in 2 nanoseconds, so we can probably run this at a 500 or 400 megahertz clock, so we can run this really fast for an FPGA. And latency, so it takes 2 cycles from input to get the output, but we can put a new input in every cycle. That's what that means. I don't think there's any instances or loops in this. And here are the resources. We're using LUTs and flip-flops only, and it's almost nothing of the FPGA. So super simple thing. I mean, you probably write this in HDL pretty quickly. Okay, so that's that. Let's check up on this guy. So we're currently initializing the design, so we have to place them around next, but we'll get there. So now if we go over to analysis, we can look at what is being done every individual cycle and the dependencies. So I like looking at the resource viewer. I don't think there's really anything useful in this. So cycle 0, cycle 1, cycle 2. You read the value in, and then you add it, then you write it. So nothing too impressive there, but this can be useful for clarifying any memory dependencies. Then we kind of have functional dependencies that this read goes to that plus, that plus goes to that plus, that plus this value is thrown in there, goes to the output. And what is this? Is this like that must be the last bit or something? Number of words to write, that's just updating the number of words, and it's dependent upon the last. So yeah, some really cool stuff. Now if we go back to our synthesis perspective, we go to implementation and we go to drivers. If we head over to hardware.h, right? So here, these are our registers. Registers 0, 4, 8, and C are reserved. Register 10 is 32 bits, and that's our value to add, and we can read and write to it. So this is 16 or hex 10 or hex 10 off of our base address, and that's how we can know to run it. And I mean, like, sometimes they provide you little functions to do it, but we're just going to do some quick memory accesses to do this and then throw in a transaction. Okay. Yeah, that seems fairly straightforward. Any questions in chat? I don't see anyone's attending right now, so that's not a big issue. So next, let us look at here. We're running route design. That should be done quickly. Let's go find that hardware trade file, right? So let's go to PYNQ 2.51 boards here. Oh no, base, LEDs, sources, block diagram, base, hardware handoff. So we have an 821. So let's copy this, make a copy, and we're going to say rename. We're going to call this LEDs. Then let's pull up our FPGA and copy that over. Xilinx, password Xilinx, and then here, boom. Nope, that's not this. So if we go over to PYNQ and we go to overlays and we go to LEDs, we can copy this new hardware handoff file over here. Oh, sorry. We can drag it, probably the easiest. And then if we keep going up, and go to LED runs, we'll have a bit file soon. How are we doing here? We're routing the design, so we'll have that soon. We can check the log of implementation. Routing is done, so we should be close to generating the bitstream, and then we can get that over, and then we can do magic HLS over and using the PYNQ. Yeah, we probably can keep this video under 30 minutes. Yeah, shouldn't be too hard. Any other news? I posted a video about PCIe stuff yesterday. It's a long video. I wasn't able to resolve an issue, but I did resolve it after the video, and I can talk about that issue next Monday, and I'll post that video as well. If anyone is interested or curious. Okay. Let's see. 5. We have a bit file. Boom. Cancel. So then we're just gonna take a copy of it, rename it LEDs, and throw it over here. Okay, cool. And let us go back to our this one, right? Where were we at? Was base what we wanted? I think base board. Then we have a DMA on the pink. So if we do this, we should get all zeros. So let's play around with this, okay? So let's do kernel, reset, clear output, reset and clear all output. Trusted. Cool. We're gonna run program our LED bit file, a new bit file, so hopefully it does it. Okay. And let me see. Do the LEDs turn on? They do. Sorry, I don't have the camera set up right now. We can do that later. Another way we can do it. So shape. I don't know why that one's taking so long. Okay, so we have some addresses. We've allocated things. We don't need to worry about doing any of the DMA stuff. Boom, boom, boom. And let's transfer. And we'll print out our output buffer. And it automatically counted it. You see? Super easy. We didn't even notice. So now let's add our HLS device. So DMA. So where was our HLS device located? Nope, this is not helpful. Address editor. So it's 8001. So let's go back to here and 8001, right? Yep. We're gonna call this HLS. And we're just gonna do HLS.write. We're gonna do address 10 and 1. We're just writing a 1 to everything. And boom. We did that. Now, input's still 0, so if we run this again, we should have 1 added to everything. And we have 1 added to everything. Well, let's try something ridiculous, guys. Let's try -1. It's an integer. We never really specified anything else. What does -1 do? Aha! Look at that. Beautiful. All F's. So we've done it. We have a really simple system, right? We have this is a great platform, right? This is a way for anyone to get into hardware, to be able to do HLS, to have DMA provide rapid input and output, and to get that going. So we have the input, we have the output, we have the control, and we made a very simple design. Super quick, super easy, whatnot. And you're like, oh, but what about the software? You throw PYNQ on it, you look at the other video, you look at this video, and we create a simple DMA transaction, and we create a little memory map IO so that we can read and write to the other control values of our HLS system. And we're good to go. We can write a hardware accelerator in HLS with DMA transactions to provide fast, powerful bandwidth for your hardware acceleration. And this is where, if you want to figure out how to do hardware acceleration, you can take some C functions, some C libraries, some C sort methods, something like that, throw it into HLS, feed it the input, take the output, and play around with it. So you can see it in action, and we can time it too, right? I assume we can time it. I'm not sure exactly when these transfers begin. I mean, send channel, receive channel, wait, and then I assume we just put time in front of it. But let's do something drastic, right? Let's do 1024, right? Let's allocate this memory. Let's get some addresses for it. We're going to write zeros to all of them. Boom. This automatically tells the size, but we can do, let's do negative 128. And we can write that to it. And maybe we had a good way to time this. We run it super quick. And then we print it out. And right there, around 100. 24. And then we can see it go and go and go and go. And we just did a massive dump of data to and from our HLS device. So this is very powerful, very easy. And then we can write wrapper functions in Python to do some cool stuff, to do some transactions to time it. And yeah, we don't have anyone viewing, so we don't have any live questions. But if you have any questions, attach it to the video. Stay tuned. I think the next part of this little series, if we can even call it that, is I'm going to be implementing some more complicated HLS functions, and we can try to see that in action to see if we can take the C thing and convert it to HLS and then run it through this PYNQ device. But yeah, for now, Beth, I think that's about it. Thank you for watching. This is a short one. I don't really feel like I try to time my videos. But yeah, it could range from 20 minutes to an hour and a half. Tune in tomorrow. Are we doing anything tomorrow? I think my next video might not be till Monday. We'll see. I may be streaming some video games, but that's about it. Have fun. Good night. Bye.